So comparison, rule of divergence, all of that is certainly important, but the main one is still this one, um, uh, the divergence test. Okay. Here it is. The divergence test. Okay, so for a series to converge, its sequence has to converge to 0. Okay, so as you can see, it sounds important. It is important. So you have to satisfy the property before you even examine the series closer. So you can look at the sequence and it will tell you sometimes, if you're lucky enough, for you to end the examination right there. So it is a common activity to, given a series, figure out its convergence. So sometimes that examination is very short. So you look at the sequence, it either diverges or it does not converge to 0, and then you're done. The conclusion is the series diverges. If it does converge to 0, then you have to proceed and do more with it. So as important as it is, not to be overestimated, because it is really uncommon. Well, I don't want to judge how common it is, but it is commonly mistaken for the end of the examination. Just because the sequence converges to 0, it does not mean that the series also converges. As you can see, the converse is untrue. That's at the bottom. Okay, so the convergence is the convergence of a series, is the convergence of the series of its partial sums. And so shortcuts that we have seen, this one is one of the biggest ones, and that is when the series has nothing but positive terms. So in the positive terms, the sequence has positive terms. So that's what it says right here. Okay, this one. And which means that every time we add a positive term, which means that the partial sums will increase. Okay. So this oscillation plus or minus, nasty sequences oscillating between -1 and 1, for example, they're out, and we have either one picture or the other. So it is either flattening out or it's not. So in one case we have convergence, the other one divergence. That's what the monotone sequence theorem says from some time ago. So this is a theorem about the sequences, not about series just yet. So so this is what it says. A monotone sequence bounded sequence converges. So that's the only thing we need to is distinguish between these two possibilities. And how do we tell it? Is there a bound or not? It doesn't have to. You don't have to know the limit. As long as you know that there is a bound somewhere, then the sequence will have to converge. Okay, so we just put it in a slightly different way. So a corollary will be about series. So we apply the every series comes from a sequence, but we do not apply this theorem to that sequence. We apply that theorem to the sequence of partial sums. So apply it to the partial sums Pn of sum an. Series sum an comes from a sequence an, create a new sequence Pn, and now we are looking at this sequence. And what if we happen to have a monotone sequence of partial sums, which under what circumstances does it happen? It is when the terms of the series are either all positive or all negative. We'll concentrate on positive, and so then we have a certain theorem. Okay, so suppose an is larger than or equal to 0 for all n. Then we have two cases. First, some an converges. So it is a number, or it is infinity, positive infinity. Okay, I made that point a few times. It is informative. It is informative to say that the limit is infinite, as opposed to simply does not exist. And we exclude that possibility when the meaning of the limit is absent altogether. And we have two possibilities for the limit that are both meaningful, and that is a number, case 1, or case 2, infinity. Okay, so there are only two possibilities. The third possibility is that on the left, it is now gone. Okay, so that allows us to do comparison better. Still loading. So one of them is familiar. So let me bring up the picture. This one. This is, as you can see from the beginning, the second row is a sequence with forming series with positive terms, and so once again there is only one possibility, whether it is infinite or not. And now it's time to actually demonstrate that the conclusion that we made has a more precise justification. That was the conclusion that 1 over n is divergent to infinity. Okay. On the other hand, other series are convergent. Okay. We just have to if we could do comparison with the right series, or in this particular case, in fact, it doesn't have to be a series. It could be an integral. Okay, so let me carry out this plan one more time. As an example, we have an is equal to 1 over n is greater than 0. So partial summation from, say, k from 1 to n, 1 over n is increasing. Okay, so then Pn is going towards infinity, or it is going towards a number. Okay, these are the only two possibilities. So we have to exclude one to prove the other, and the idea is here we compare it to the integral. Okay, to the integral of function 1 over x. Okay, so replace n. Well, it's not 1x, 1x plus 1, 1 over x plus 1. Okay, so. So Pn is larger than or equal to, well, actually we don't have to do any kind of comparison. Since we have only these two possibilities, so we have to demonstrate that it does not converge. Okay, we have to demonstrate that it does not converge, so we do have to carry out this comparison. So the summation, or rather, Pn will be larger than or equal to integral from 1 to n of 1 over x plus 1 dx. Okay, so I'm not sure. Do you see this this picture here? The top line is function is 1 over x, and y equal 1 over x. Okay, the second line is my series. So suppose I reach n over here. Okay, so then the purple thing is this thing over here is Pn. the sum of those purple bars gives me Pn. After n steps, I add n terms, and that gives me Pn. Okay, so my graph, that red graph, you can see how it appears below my staircase. So this is it, like this. So that's the same thing. I just bring them together, and my 1 over x plus 1 will be in the will be below the staircase. This is 1 over x plus 1. 1 over x plus 1. Okay, so okay, why? Why? Because of the formula, right? So well, one bar at a time. In other words, one bar at a time. If I take every bar is 1 over n, this is how things starts to adapt. So what is 1 over n will be larger than or equal to integral from n to n plus 1 over x plus 1 dx. Okay, so if you zoom in here on any of these bars like this, then the height of the bar is 1 over n, okay, and its area then 1 over n times 1, right? So 1 over n times 1. But the graph, the red graph, is going will be lower than that. Okay, so then what we do is what we did last time. So then we integrate. This thing goes to, rather it does not go to as much as well, we just go ahead and compute. We don't really need the integral that as much as we need the computation. So we just integrate, and we have ln x plus 1. Okay, from 1 to n, which is ln n plus 1 minus ln 2. Okay, so as you can see, we still have this inequality. So now integral is taken care of, and we just have Pn, our increasing partial sequence of partial sums, is larger than or equal to a certain sequence that goes to infinity, right? It goes to infinity as n goes to infinity. So then the conclusion is, based on our analysis, a sequence that is increasing, and it is kind of a push from below by a sequence that goes to infinity. So the conclusion that the whole thing goes to infinity. Pn goes to infinity, which is translated into our common language of what we of series. We have infinity. So our sum is infinity. Okay, so before we go to the theorem, let's turn it around, and well, let's just look at this computation and see what kind of an well, let me try this. What I've put s here. So 1 over n s. So I want some power, change the power of n from 1 to something else. So what if s is, say, less than 1? Say, how about s is equal to 1/2? What's going to happen to this computation? S plus 1/2. Let's just go with 1/2. So 1/2 square root of n. Integral will be different. What's going to happen if I integrate in x plus 1 1/2? What happens to the power? X plus 1 or negative 1/2. I integrate. What do I get? Powers under integration go which way? up, or by 1. Okay, so it will be x plus 1, 1/2 divided by, well, by 1/2. Okay, so it doesn't really matter, all of these details don't matter. What matters is its limit. Where does this function go as x goes to infinity? Square root. What do we know about the square root function at infinity? What? Infinite, right? Yeah, so it goes, even though it flattens out, but it goes to infinity, so it is infinity. And just like over here, so it appears the same plan works out, even though the function is slightly different. But in fact, the function is larger than the original, right? Because square root of n is smaller than n, which means that this function, if this modification makes the function larger, then no surprise, the whole result, the series is bigger, and therefore, if it was going to infinity, it's still going to infinity. Okay, and we just confirmed that with this analysis a little bit, with integration. Okay, so that's another case of when you have a divergence in that case to infinity. Now, how do we make it convergent? Once again, we can just change the power of s. We change s to a number that is larger than 1. How about 2? What's going to happen if I have here n squared in red? Okay, so I have 2 here. I have a negative 2. If I integrate negative 2, power goes up by 1. What I'm getting is, what's the power? Negative 1. Where does it go? 1 over it's 1 over x plus 1, right? So where does it go? One over x. It goes to 0. So as you can see, that that does not work out anymore. But that plan doesn't work out. Our conclusion then will fail. So we have to be careful here and not to say too much, and do not try to claim that we have proven that our series converges, because we cannot. But why not? Because if you look at the inequality is still there, right? Look at the inequality. So we have demonstrated that our partial sums are larger than a certain integral which converges. Certain improper integral that converges. So our series is bigger than a number. It means that it could still be infinity. Okay, so which means, what do we do? How do we? I want to demonstrate that 1 over n squared is a convergent series. What do I do? One over n is divergent. 1 over square root of n divergent. It is taking care of this substitution, substituting series with an integral. I want to follow the same plan, but I want to prove the opposite. So I cannot just modify this easily. I have to do more and more than just modify integration. What else do I need to do? What should happen to this inequality over here? Well, we're trying to prove convergence, which means we have, and the theorem is right there. As you can see right there, we need to demonstrate that it doesn't go to infinity. But how do we demonstrate it does not go into infinity? We can demonstrate its boundedness. Okay, so the exact opposite story. So the inequality would have to be reversed in order to prove anything we want. Okay, so as you can see, that picture changes. That picture, that's the bottom row on the right. What happens to the graph? What should we do with the graph? What should we compare our sequence with? The opposite inequality, what does it mean about, what does it tell us about the function, at the top, the first row? What should happen to the function? Well, we are the blue staircase is unknown. We don't know what's happening to it. We are comparing it to the red curve that we do know what's happening with. So how we are pushing our graph from below, in this case, with the red graph to show that everything goes to infinity, because the red one goes to infinity, the sum underneath that graph. Now we have to push down. Okay, so we have to put our graph here somehow, like this, above our staircase. Okay, so which means that the function then would be y equal to not 1 over x plus 1, but what? It's the same graph. We don't have to invent a new function. It's the same graph, except in the former case it was shifted left. We're not shifting down, by the way. We're shifting left and right. So we're shifting left. We shifted the left curve to the left, the red curve to the left, and the blue one is the same, shifted to the right. Okay, so let me put it this way. So we start with 1 over x function. Let me start over. So if I have y equal, the red one is 1 over x, say. Okay, then I could go to the right in order to get that. I'm sorry, that's not right. What I meant to say is you start with the graph y equal 1 over x. Okay, and then if you push it to the left, I push it to the left, so it would end up underneath our staircase. That function is y equal 1 over x plus 1. Okay, now I have to push it to the right, which means that it will be 1 over x minus 1. So remember that in pre-calculus, plus minus 1, replacing x with plus or minus 1 shifts the graph horizontally. When you give a plus, it shifts to the left. When you give a minus, it shifts to the right. So once again, it is an important thing which way it's not shifting vertically. And that would be cheating, but we are shifting. So that is my black curve here, and it is shifted to the left to produce the red graph, and it is shifted to the right and to produce the blue graph. Okay, so let me make that picture again here. So let's say 1 over let's have my staircase first. This is my staircase, 1 over n. Okay, and then I put 1 underneath it, like this. And this is y equal 1 over x plus 1. And then I do a very similar thing, but with my graph is now the second example, different from the rest. So this, by the way, the same applied to y equal 1 over square root of x plus 1. Works out the same way. And now I'm talking about 1 over what? 1 over n squared. 1 over n squared. This is my staircase, and it is 1 over n squared. Okay, and then I'm trying to add up these bars, the areas of the bars, and then I need to put the graph above it, and so I put it like this, and this is y equal 1 over x minus 1 squared. Okay, so the inequality that we already demonstrated for the last example here, what I'm talking about is 1 over n squared is less than or equal to integral from n to n plus 1, 1 over x minus 1 squared dx. Okay, so it is visible if you zoom in on one piece of the graph. I have a picture here somewhere that illustrates the idea. Where is There it is. Okay, so that is on the left is my sequence, whatever that sequence is. And now I could take the same graph. Where does the graph come from? I'm taking the formula for an and replace n with x. Okay, so if it was 1 n, I have 1 x. Okay, so that's a starting point. But then, as you can see, I have two curves to use. Well, actually, it's slightly different from what I just explained. You actually do not have to shift. You don't have to shift to the left. As you can see, the top picture shows you can just take the function itself, right? So because the function assumed to be, that it certainly is a big assumption, that f has to be decreasing in addition to our sequence a and b is decreasing, okay? Certainly not the same thing. So if that is the case, then you can see what's happening. I'm replacing a and n with x. So whereas my formula is this, f of n is equal to a n. That is the relation between the two sequences. Okay, between sequence of the function. I start with a sequence, then I produce a function. If I just replace n with x, I have my function that touches that top middle. It just touches the corners of my staircase, okay, and then then all the bars are below, and then it sums up to whatever it sums up to. You compare the purple interval here to this green curved region on the right. Okay, so and then so this is the an. This is an, just a single term an here, and this is actually, remember what this is. This is an integral, right? This is an integral of f dx from n to n plus 1. Okay, and the inequality, as you can see, is you can see it on the right, is fairly transparent. So this is what I'm talking about, this part. Okay, so there's a bigger for each of these bars. There's a bigger area under the graph of our function, if you would put it appropriately, or there's one smaller if we shift it to the left, which is what is happening in the latter case. The second one, as you can see, I have f of x plus 1. The graph shifts to the left, and instead of touching the corners of my stairs, as you can see, this is where it is. It is right here. It touches whatever that is a staircase. What do you call that part? Not rather than the outer corner, it touches the inner corner from the inside. So it's below the staircase at all time, and that's why the second inequality is here. Whichever you need to prove either the divergence or convergence. The plan works as long as you can handle the integral. Okay. So once again, it's one bar at a time. But that's what it shows. But when you put them together, you're facing this picture. Well, one of the two, either below or above. Either way, it works out. And once you have one bar at a time inequality, you see it on the right. Then you can also do then you add them together, and you have on the left, or rather, this one will produce partial sums, right? If you add all of them together, and these two will produce integrals. They produce integrals just of two different functions. Okay, so let me correct myself. I don't really need to subtract. I don't need to subtract minus here. I don't need it. Okay, so same here. I don't need to. Just 1 over x plus 1 is fine. 1 over x squared is fine. Okay, so from n to n plus 1, this is what an is. That's the picture illustrated on the right. I have my sequence. An is 1 over n squared. I replace n with x, and also replace my term n with one little integral. But if I now add these together, what do I get? I have Pn here, and I have integral from 1 to n plus 1 there. Okay, so as you can see, we are getting the opposite inequality from what we had in the former case. We are bounding our partial sums from above. Okay, by integrals, and then we'll just see where it goes. Where does it go? We integrate. If I integrate this thing, 1 over x squared, so I already did. So it will be 1 over what is it? Negative 1 over x from 1 to n plus 1, and which is 1 over n plus 1 minus plus 1, 1. Doesn't matter where it starts. It appears to converge to 1. We are not saying, that is the word of caution here, is we're not saying that Pn converges to 1. We cannot tell it. We only know that A, if it converges, and that the sum will be less than 1. So the inequality still is there, but does not turn into equality because, well, how do you know? So all we can tell is the convergence by our theorem, and secondly, we have an estimate. We have an estimate of the sum. It's a bound, so it's not necessarily very accurate. So let me state the theorem, which is called the integral comparison test. The integral comparison test. Okay, so we start with a function because the series might appear from anywhere you can imagine, and so we want to so whether or not there's an explicit formula, maybe not. So we're starting with a function. So f is defined on an array 1 infinity. Okay, and an is equal to f of n for n from 1 to infinity. So that's how you make a sequence from a function. Okay, and then there are conditions that have to be satisfied. Okay, so the function has to be continuous to begin with, so that we can integrate. Second of all, it is decreasing. It is crucial that it is decreasing, as you can see. Especially, you can see here, imagine on the right, if the function is not guaranteed to be decreasing, is not required to be decreasing in the first place, it might do something like this. It might dip. Okay, and then our inequality is out of the window. Inequality of comparison, this inequality that you're looking at, that the bar is smaller, the area of the bar, the purple bar in the middle, is smaller than the green area on the right. But it only is guaranteed when the function is decreasing. If not, there could be a dip, like you see here, and look at the area. Look at what happens to the area. Like this, it becomes too small for comparison. So even though the function is produced in the same manner as we have required, the area is not smaller anymore. The area of the bar is not smaller than that area, the green area. Okay, so that's why we have to require it. And thirdly, it is, well, once again, we have to require again that it is non-negative. It could be 0. That's not a problem. But all of these three are required. Then what? Then the improper integral of f integral from 1 to infinity fx dx, firstly, and the sum of the series sum an from 1 to infinity, either both converge or both diverge. So it's a pretty good test because it works both ways. So once you have a function replacing your sequence, then you have the answer as long as you can handle the integral in the first place. And we just did. So we did it with what? We did it with powers. So there is what follows from the test is the test for p-series, so-called p-series. P-series is simply the summation 1 over n to the p, and from 1 to infinity. Okay, so 1 over n is the harmonic series, and the rest have no special name other than collectively they're called p-series. So p is a parameter, and it is any real number is applicable. Okay, so that's a p-series, and now based on this theorem, on the integral comparison test, we would do what? We would replace this p-series and with an appropriate integral from 1 to infinity, 1 over xp dx. So once we do that, we can evaluate that integral and find the answer is once and for all of these series, regardless of p is. Why? Because we can handle this integral. So 1 over xp is just integrated, power goes up, so it will be, what is it, negative p, 1 over xp minus 1, from 1 to infinity, and then we already did the hard work. We know what the answer will be. If it is 1 or less, yes, if it is 1 or less, the power, if it is 1 or less, then the power will be larger than 1, right? Larger than 0. So p is equal to 1 gives me a bunch of numbers. But if it is larger than 1, it will be convergent. Strictly larger than 1. If it is strictly larger than 1, all the powers, then the power in the denominator will be positive and the whole thing goes to 0. So it is equal to, so it converges. Let's use infinitives here. So it is less than infinity if p is larger than 1, and it is infinity otherwise. Okay, so, well, that means it's like piecewise function. There are two cases. Depending on the value of p, and then you have your convergence. Okay, so the test is then a p-series converges for p larger than 1, diverges for the rest. Well, let's just say, do I want negative p's? I guess not. Let's just say p between 0 and 1. 1 is included. P larger than 1. P larger than 1. The convergence. P less than or equal to 1 is divergence. So that's the p series. It is a shortcut. It certainly follows in pretty much one-line computation from the integral comparison test, which is really where the magic happens. Is this indirect proof with some applications of our understanding of limits, our understanding of decreasing sequences. Monotone sequence theorem, as well as this picture over here. So we carefully squeeze. Let's face it, we squeeze our function between, we squeeze our sequence between two functions, which is the same graph, only that function has the same graph, only shifted. I have here's a p-series illustration of the p-series. So that's a summation. These are sequences of partial sums. As you can see, p is equal to 1. You can't really tell from this, but certainly p is equal to 2. It flattens out really really harshly. That's so at the bottom. On the other hand, p equal 1 we know to be divergent, but look at how flat it is after, what is it, almost 1,200 steps. It still looks it looks flat, but really not. It's certainly not as flat as the previous one. The rest of them go to infinity fairly fast. You can predict that, even though every one of them will eventually flatten out. That doesn't change anything. Okay. Okay, it's a little bit more of comparison. So this is a convenient tool, but not really applicable unless you have some manageable formula in the first place, and we really cannot limit ourselves to that entirely. So we have more comparison. We already did that similar for between integrals, and now in sequences, now series. Okay, so it's called the direct comparison test. And it is, once again, carefully applied only to positive term series. So suppose we have two series, or two sequences rather. Okay, or all n. So the idea is the same as which one? This one. You can imagine the comparison that we carried out was specifically between a series, a sequence, and an integral, so that function f was continuous, as a matter of fact. But if you imagine that you have zoomed out so much that you cannot see the stairs of that, you can imagine that the first row is also staircase. It's just stairs are just so short that you cannot you can see them. The idea still applies in exactly the same manner, and that's what this test is about. So let's put it this way. One is convergent, the other one convergent, and vice versa. We just have to be careful. So the analysis that we already did, we did both two cases, case number 1 and case number 2. So suppose sum Bn convergent. Well, let's say less than infinity, because it is fair when you deal with a series with non-negative terms. Then the only thing that you have to say is whether it is equal to infinity or it is less than infinity. Less than infinity simply means that it's a number. It's a number, that's one way to put it, or you can say it converges. It's the same thing, but it is really because we have this extra restriction available, which is, so it pays off then to have this restriction, because now the language is simpler, because instead of 3 cases we have only 2. And so as long as Bn is less than infinity, so the series is convergent then to a number, then we can go backwards and say that the same is true about An. As you can see, the inequality is suggestive. I'll look at it. If I try to translate the original condition is about sequences, but if I start to add them up, the partial sums will still satisfy the same inequality, right? This inequality. Well, let me indicate the proof here. So Pn is the partial sum of An, and say Qn is the partial sum of Bn. If I start adding them up, I still have this inequality, Pn less than or equal to Qn, right? So because the original inequality there, I can that relation is preserved. And then I know that Qn, look at it, Qn, no matter how many terms I add, according to the assumption in case 1, it is less than infinity. It's not just less than infinity, it is in fact less than some number, I don't know, m. because Qn is convergent. That's what sum Bn less than infinity. That's what it means. It is the series convergent. It means there is some number at the end, and let's say that number is m, the sum. Okay, so then, and as you can see, what happens, what you observe about Pn is, on one hand, it is increasing. We know that, and then also bounded. Increasing and bounded, it is convergent then. Okay, so, and then that is the case number one of our theorem right there. Give us the conclusion. Okay. On the other hand, so that's case one. Convergence of the second sequence of the biggest sequence implies the convergence of the smaller one. Okay. Now, if I go the other way, what's the other way? With the same inequality, what can I say about the convergence of sequences? The convergence of the biggest sequence implies the convergence of the smallest sequence. Can you have a similar statement about divergence?
Would it be the divergence of the smaller sequence
Right.
implies the divergence of the...
Yes. The divergence of a smallest sequence, like this, right, implies the divergence of the largest sequence. Okay, so indeed, as you can see, the inequality, the implication points in the opposite direction, but it works in exactly the same way. Why? Because look at it, we just did it for those particular examples, but as you can see, it works out the same way, P, and so this is case one. And now if I'm looking at case two, I have still the same inequality, Pn less than or equal to Qn, but this time what? Pn actually goes to infinity. That's what divergence means. So as you can see, Qn is larger than a sequence that goes to infinity, so it is unbounded. Unbounded means divergent. Okay, so larger than a divergent sequence to infinity, then it itself is, which makes it unbounded, which means that it is divergent. Okay, so we'll do some more of the examples of this. It's quite often applied to series. Okay, so I'll see you tomorrow. The test, the final is it Thursday? Is it?